When periodic waves with the same shape, amplitude, and wavelength travel in opposite directions in a linear medium, such as a rope or a spring, they produce a distinct pattern in the medium that appears to be standing still. So I had a couple students in the class try to demonstrate this, but before they did, they first sent down one transverse wave. So you see a bump traveling from one side of the slinky all the way down the room to the other side. Then they did the same thing for a longitudinal wave where they just compressed all the slinkies and pushed it down and back. Then I said, all right, try to do the same thing. And when they're able to match each other, and that means matching the same amplitude, wavelength, and speed, we got what was called a standing wave. And it's a pattern that kind of looks like this, where you no longer see the wave traveling one way or back. It looks like it's standing still. And there's some interesting points. One of them is a node. So there's certain points which don't appear to be moving at all. And then there's what we call the antinode, or a loop, because it makes it look like almost like a big loop. So the loops, this part of the slinky travels all the way down and then back up, and then down and back up. Now the nodes, if you think about a wave, okay, a wave goes from, you grab it pink, say up, down, and then right back to here. So that's one wave where it just goes up, down, and right back to the starting point. If we look at from node to node, that's only half a wavelength. That's half a wave. It says antinodes or loops. They're between each node. A point in the medium called the antinode vibrates maximally. So that means this little point here vibrates all the way down and back, or rotates down and back. So nodes appear to not be moving. Antinodes or loops move a lot. Let's try an example now. It says the distance between two successive nodes. Now the word successive just means one after another. In a vibrating string is 10 centimeters. The frequency of the source is 30 hertz. So we're looking for two things, the wavelength and their velocity. So when we're doing these questions, it's good to draw the standing wave. And I'm not very good at this. So we just kind of go up and down, up and down, up and down, and then the other way. Definitely not very good at drawing that. Anyway, so if I looked at, say, that node and that node, what I know about that is it's 10 centimeters apart. So that's 10 centimeters from one end to the other. Well, how much of a wave is that? If my wave started here, I'm going to draw that in green, it would go down and back. That's actually half of a full wavelength. So let's write that down. So half a wavelength, we know, is equal to 10 centimeters. But I don't want half a wavelength. I want a full wavelength. So the opposite of dividing by 2 would simply be to multiply by 2 on both sides. The 2's cancel out, so I end up with lambda is equal to 20 centimeters. So this is part A. Part A said, what was the wavelength of the wave? It's also common sense. If I know from node to node is half a wavelength and that's 10, well then obviously a full wavelength would be 20. In B part, it wants to know what the velocity is, or the speed. Remember that sound waves is always uniform motion. We never have to worry about acceleration. So let's write down our given information. I know lambda is 20 centimeters. I just figured that out. What else do I know? I know the frequency is 30. So frequency is equal to 30 hertz. And finally, I'm actually looking for the V. So V question mark. Well, the wave equation is V is equal to lambda times frequency. There's a problem here. Lambda is 20 centimeters and it should be in meters. So 20 centimeters is the same thing as saying 0.2 meters. So when I put the lambda in, it's going to be 0.2 times the frequency, which is 30. And when I put that into my calculator, I end up with 6 meters per second.